Hello everyone, I'm Andrii Kuibarov and I'm one of the master students who came here within UKRATOP project, and today I'd like to tell you about topological aspects of electronic structure of bismuth tellurium iodine. But before I start, I would like to say thanks to everyone who was involved in my stay here in Dresden, especially Dr. Borisenko, Professor Buchner, Dr. Fedorov, who helped us with experiments at BiTeI, Volodymyr, Yevgen, and Zhonghao, which spectra I used to do my work. Also, everyone in Berlin, in BiTeI, who helped us during measurements. And on synchrotron, it's really hard, so we couldn't do it without them. Uh, Dr. Alexander Yaresko, who helped us with the DFT calculation, and Helmut Berger for providing simple crystals for our measurements, and of course everyone who was involved in creating the UKRATOP project. So we have such an opportunity to have a real hands-on science experience. So before I start, I'll just make a quick summary of what I've done here, not only my BiTeI related job, but also other. So I was 3 times on synchrotron here in Berlin on BiTeI, and I measured on 2 beamlines. First beamline new. On this beamline, we were testing our new equipment, Fisuma, which allows us to see the whole Fermi surface at once. And other 2 times, I was on the 1Cube station on Berlin, and also, of course, and also I did my measurements here in the IFW Dresden lab. We have here new laser, so we're right now like adjusting this laser, and you also can see the picture of 2 kelvins which we have in our lab, but this is a little bit cheating because actually we can stabilize only 3 kelvins, so it's just a picture. So I would like to start my presentation with Moore law. Everyone knows what is Moore law. It says that every second year the transistor density should increase twice. And until recently, this law was correct, but right now the conventional semiconductor technologies have huge problems. For instance, that lithography is very expensive right now in the vacuum. So if we want to continue scaling down our transistor, we have to come up with new ideas how we do it, and or with a new approach. And there are different types of new approaches. For instance, we can say we can make new computers based on Josephson junction, or for instance, we can use memristors, or for instance, we can use quantum computers. There are different approaches, but what is the common for all of these approaches is that we need new quantum materials, but not, I would say, not new quantum materials, but materials with new quantum properties. So it might be materials that we even know before, but we didn't know that quantum materials. And what is the best way to investigate, to find out new quantum properties is, of course, to investigate its electronic structure. So I would like to start with the electronic structure of BiTeI. And this is a picture taken from the article released in 2011 in Nature Materials. So if you see in the middle of screen, you can see that BiTeI is a semiconductor because it has this gap on the Fermi level. But if you take a look on the right hand side, you can see that it has metallic property, metallic conduction. Why? It is because of self-doping, because non-stoichiometry and self-doping, and the actual Fermi level is raised above the one which we calculate with DFT. And on the left-hand side, we can see the first ARPAS data released in this article. So this is the conduction band, but in our team we call this McDonald's or Volkswagen. You can see. So, how did we start measuring BiTeI? It was simple. We just wanted to measure some shiny crystal when we were testing our Fisuma device. And while we were measuring, I heard from other people that this material has giant Rashba splitting. And I started looking, what is this giant Rashba splitting? And I started looking, what is Rashba effect? So Rashba effect is apparently the lifting of degeneracy, of spin degeneracy of parabola. It's caused, the idea is that when electron moves in the electric field, in external electric field, it creates its own magnetic field due to Lorentz transformation. In its magnetic field couples with electron spin, and therefore the degeneracy is lifted. So you can see the picture on the left hand side. You can see the band with the spin degeneracy, and on the right side you can see how does parabolas shifts along the momentum axis. But the thing is that the confusing thing is that the Rashba effect is two-dimensional effect, and on this article they were talking about bulk Rashba effect. And what I found next, that there is an article which says that that what they did measure on previous article was actually a surface state, because there is such thing as a universal curve, which say that it is impossible to measure bulk with ARPS with energies starting from 20 to 100 electron volts, because if you can see, if you take a look on this picture down below, it's called universal curve. Its minima is around 15 electron volts, and it says that we can probe only something about 5 angstrom, which is really small. So yeah, the point is that there is a controversy between, there are two groups. The one who says that it is a bulk driven bands, and the other one which says that it's surface state. So I've just decided to make a little investigation, which what is this in real life. So I've decided to destroy surface states. How did I do this? I've just clicked my sample not in the main chamber where we actually do our measurements, but in the preparational chamber or fast entry, where pressure is 2 degrees of magnitude worse than in the main chamber. And I left my sample there for 2 hours, and after that I've measured it. And as you can see, picture didn't change a lot. Actually, it is almost the same that I've shown before on the on the article, which is clear evidence of the thing is that is which is clear evidence of those bands having a real bulk nature. But it was not convincing, and I decided to measure actually a laser spectra. We have here in our lab 6 electron volt laser. So we measured the sample with 6 electron volt laser without any special surface treatment. So I've just left my sample right in the main chamber, and as you can see, there is no difference. There are almost no difference, because like it is different samples, but from the same batch, of course, and like different light source. But the thing is that those states are the same, which is clear evidence of those states being bulk. And also, we have measured Fermi maps while we were on a BiTeI, and as you can see, those maps does really change from 19 to 21 electron volts. And if it were a surface state, it shouldn't be like this. Like we shouldn't see any changes at all. So yeah, and the other thing which confirms that it is a bulk band is that we see threefold symmetry and at 19 volts. It is because the crystal structure of BiTeI, the bulk crystal structure of BiTeI, says that we have to see threefold symmetry, and if it were a surface state, we have to see sixfold symmetry. But actually, if you can see on the 21 electron volts, we see sixfold. Like we have a hexagonal on the 21 electron volts. But we remember that we also measured the same spectra with Fesuma. So here is a picture taken with Fesuma. This is a device, again, which allows us to see the whole Fermi surface. If you want to measure Fermi surface with an ordinary Siente device, you have to scan the polar angle. You have to rotate your sample along the polar axis to create the polar map. So you just basically are measuring different spectra and then combining them together. And while using FESUMA, you don't have to do this. You see the whole Fermi surface at once, and you can also see on this picture the same, that there is a difference between 19 and 21 electron volts, and you can see the threefold symmetry also in 19 volts, which is also an evidence of those states being bulk deriven. No, yeah, this is one on basis, this is one on mean beamline. So at that point, we were already quite interested in BiTeI, and we asked Alexander Yareska to perform DFT calculation for us. And what we've seen was really interesting, because the DFT calculation which he did was quite different from one which we already seen in the article. And the main difference is that it's not a semiconductor, it's semi-metal right now. And the thing is, so if you, on the left-hand side is the DFT calculation performed by Alexander, by Yareska, and the right-hand side DFT calculation from the article. So like right now, there is no band gap anymore. You can see between gamma and A points, there is this band crossing. And we started investigating why is it so, and we found out that actually when they did this DFT calculation, they swapped tellurium and iodine atoms. So we did our calculation with the structure taken from experiments, and they did their DFT calculation by swapping iodine and tellurium atoms. They say that because of iodine and tellurium atoms are close in the periodic table, experimentalist my deep mistake, and just and that's why they changed it to. Yeah, they say that it's also theoretically more stable. It has less. Yeah, that has inversion. Like right now. Yeah, it has inversion in reality. Broken inversion symmetry. I'm saying, yeah, I'm sorry, I'm just didn't understand the question. I was saying that if you change, if you swap the atoms, it also has broken inversion symmetry. So in every, like if you change, if you swap those atoms, you will only swap the distance between iodine and tellurium atoms, and iodine and iodine and bismuth layer, and iodine and bismuth and tellurium layer. You will just say that one is closer to bismuth than other if you swap those atoms.
Could we take different structure with that?
Yeah, they did.
You can use any kind of structure to take some structure which doesn't exist.
This is theoretically more stable.
Yeah,
but I know we now understand it, because the part was big and it was giant only in that case. Its focus was not efficient.
Yeah, like in our calculation, we also have a Rashba splitting, but not as large as they did have in their calculation. And what we did next, we measured copper doped BiTeI. Why we did this? Because there are a lot of information in the article that if you apply pressure to BiTeI, it might have a quantum phase transition, and it will be a topological insulator. So I thought that if we dope a sample with copper, it might intercalate in the crystal lattice, and it will be the analog of chemical pressure. So why not to measure copper doped BiTeI, taking into account that there are no RP spectra of copper BiTeI in the, I haven't found it anywhere. So like right now, you can see on the left hand side RP spectrum of the copper doped BiTeI. And the one thing which is clearly at the beginning is that the high of this McDonald's is smaller than it was before, and it should be like this because copper doping for this crystal is Hall doping, so we just shifted down our Fermi level, and also we measured Fermi map, which is right in here, and it has 23 electron volt, and it has hexagonal shape. So And what we did next? Next, we measured the dependence on the energy. So we just stayed in gamma point and increased our energy. And what we saw was on the 28 electron volts, we saw something in the band gap. So you can see in here that at 28 electron volts, there is Dirac, we call it, there is some bands at the band gap and it disappears at the other energies. But we did only measure from 15 to 30 electron volts. So I think we haven't like called the whole Brilliant zone. So yeah, but the thing is that we can clearly see that there is something at 28 electron volts and there is nothing on 16, 25 and other electron volts which we measure. So, and this is the evidence of the DFT calculation which made Alexander Yareska. Like we've seen there some crossing. So I believe that right now we can say that we have evidence of BiTeI being not a ordinary semiconductor, but rather being Dirac semi-metal at that point. I also made
Sorry, that was too fast for me. Can you explain once more? What should I take from this?
okay. The thing is that previous DFT calculations suggested that this is a semiconductor and it has band gap. Like on the right hand side, you can see there is nothing in this. There are no bands in the band gap. And what we see is at the 28 electron volts, it's clearly seen that there are some states which there are some states, and at other energies they disappear. So I believe that it is an evidence of this material being three-dimensional Dirac semi-metal.
So what you see is KZ dispersion.
Yeah, this is
That's the message.
yeah, this is a case.
Sure. The rest of calculations, zoom in, so you see each set is pretty direct.
Yeah, yeah.
And it's hard to see this.
Yeah.
You have to zoom in. Between gamma and
So yeah, you
there are
can
bands which cross.
you can see here band crossing. So in our DFT calculations there are band crossing, and on the other DFT calculations there are no band crossing.
It would help if you zoom it, if you present it more zoomed, present all the data in
experimental relax or experimental.
Yeah, I have 2 slides more, and I'm over. Can I? Just... So I also measured KZ dispersion, the peak width. I mean, peak width is the distance between this ends of parabola and the left-hand side of parabola and right-hand side. So, and we can see that there is a little dispersion, which says against in favor of those states being bulk states, but not surface states. But if we had surface states, it wouldn't be like this. And yeah, that's all. Just quick summary is that of my work here under UKRATOP project that I've been on 3 BIM times. Like I've spent about 1.5 months at BESI. I took part on testing new Fisuma device. It was actually 1 month after I arrived to Dresden, so it was cool. So we're now tuning our laser in the lab. You have seen spectra, and of course we found proof of BiTeI being not an ordinary semiconductor, but rather a 3D Dirac semi-metal, which ordinary DFT predicts. So thank you for your attention.
So we are open for questions. If we cannot hear you, please write them on the chat so that.
So who will give the right for questions?
I just want to comment that it's really also calculations. This was a technical sort of take of crystal from the box, which is nearly 20 years old, and we need something shiny to test everyone, and that came out. We always have a sort of, and then of course we needed for this technical thing good calculation so that we compare with our interesting experience than it was.
We have very detailed calculations of pressure because it has what's called very curvature dipole. And essentially, if you have doping and very curvature dipole, we can pressure. Just check. We took the experimentally reported experimentally reported pressure.
But I think it's only one.
Yeah, there's only one.
Or about I want to.
Because when Sasha takes the
I have additional slides, for instance, showing that we doesn't did something wrong, because when Alexander Yaresko took the swapped system, he get the structure as it was in the in the article published in 2011. So it's not like we just are mistaken in our calculation because we didn't.
So that Yaresko probably gets also different Fermi surface, right?
This is the point. This was the point. We saw this Fermi surface near the low energies. And this is not what is expected with this.
Yeah.
Then of course there was confusing our first result that you guys see on the surface, so we have to first tackle this. Because if you see if this is on the surface, then it's no surprise that you see across all energies. But first, that's why we saw first the question whether the surface is bulk. And then there's evidence that this is bulk, and this bulk from the surface is not consistent with this one. But this one is extremely tricky.
Yeah.
That one really stays like McDonald's wall.
I would also say that there are the Gauss-van Alphen experiments, which says that the Gauss-van Alphen experiments shows us that when we rotate our sample, it doesn't get any saturation, which says that this Fermi surface might be two-dimensional, like quasi two-dimensional.
Also optical data. I mean,
Yeah.
we wrote on a lot of papers with the optics, the Gauss-van Alphen, and sort of the story coming out from Nagaosa and Narita originally that it could be revisited because they showed the optical data from some, for example, to go, there is edge, it's slightly depth, but when you read more carefully, you understand that it's actually not straightforward. There's no following directly to the The Gauss-van Alphen clearly shows one paper on the Hellman-Darker crystal that is more
They are saying that
this is stated in our right?
Yeah, they stated right.
Phenomenon is state, right? So we're seeing this interesting story.
Interesting story, yes. I agree. And the copper doping, what does it make with this Dirac form? You know that?
So the copper should make the whole doping, but
at that point, I believe that copper doping didn't make the Dirac point. It just shift down our Fermi level. But I believe if we measure an ordinary sample, we will get the same result. We just didn't.
So the Dirac point seems so far only the copper doping sample?
Yeah. Because just because we didn't measure the ordinary sample with the original.
But that would be the next plan to do it, and then
we plan to do it from ordinary sample and see where it is to that process distribution. Because as Rune said, the interesting pressure, and this is chemical pressure, I don't think chemical pressure here.
That's another question.
But the reports of
just chemistry. Is it intercalated, or is it replacing something, or is it added? Do you know that?
Does the C-axis change? The C-axis distance?
I don't know. We didn't perform.
This was another 20 years old box.
Yeah,
That's
a
a
whole
whole big box. I have no idea. I could ask Helmut. From last century.
So Oksana had a question from the audience online. I don't know if you can hear her now. So
Hello, thank you for your talk. Could you please tell more about DFT, what it means?
Oksana, can you hear us?
Yes.
Yes, and I can hear her. Could you hear her or what?
No, can you please repeat?
Hello, thank you for your talk. And could you please tell more about DFT and what it means? And did you use your experimental data to make this calculation?
Okay. understand the question. More about DFT. So DFT calculation is just calculate the electronic structure. I didn't perform it myself because I think this is work for for theoretical physicists. What we do, we ask the Dr. Alexander Yarescu to perform this experiments. And this is just show us clearly what we measure with ARPES. So you can see here that DFT calculation is just energy versus momenta. Momenta in different direction along the symmetry lines in the Brillouin zone. I didn't use my own experimental data to calculate DFT. To calculate DFT, one needs to know crystal structure. So you have to perform, for instance, you have to somehow know the lattice constant, and we've just took it from the literature. It was measured like 15 years ago, even before it was known that this material does host giant transverse splitting or something like this. So the answer is no. I didn't use my experimental data to perform DFT.
Thank you, Andrii.